Hello everyone and welcome to my channel Network Bytes with Laksh. Today we are going to look into a new topic in OSPF and that is link state advertisements. But before we move on into the discussion, let us just have a small recap of what we saw in the earlier video. In the earlier video, we saw how we can deduce some information about OSPF through its full form. OSPF stands for Open Shortest Path First. Open means open standard. Shortest Path First or SPF is called as the Dijkstra algorithm with which OSPF uses to find out the shortest distance between the source and the destination. It's a layer 3 protocol. It's a classless protocol. It supports classless address masks. Its AD value or the administrative value is 110. It uses a multicast address of 224.0.0.5 and 224.0.0.6. The multicast address of 224.0.0.6 is going to be one of our discussions today. We also saw the difference between a link state protocol and a distance vector protocol. OSPF uses a concept of area. It also supports ECMP, right? And it uses this Dijkstra algorithm through a formula called as the metric formula, in which OSPF uses the reference bandwidth divided by the interface bandwidth to calculate its total cost to reach from a source to a particular destination. Then we also saw a comparison between EIGRP and OSPF as to why EIGRP is used in the enterprise side and why is OSPF preferred on the service provider side. And then we saw about the OSPF network types. Uh, those are point-to-point network type, which is basically used in the serial interface. The other is a broadcast network type, basically for Ethernet interfaces, and stub network type, which is usually for loopback interfaces. Then we saw how two OSPF routers can become OSPF adjacent routers in a serial interface or a point-to-point network type. We saw their configuration of how to enable OSPF using the command line router OSPF1, and then we saw how router ID is chosen by any particular router, what is a router ID, and what is the election criteria or a tiebreaker criteria to choose a router ID. We also saw how a network command plays an important role in advertising a particular network through the interface that the network command is used for. And then we also saw about OSPF states, wherein two routers, when they are trying to become adjacent routers, how OSPF plays different OSPF states and goes through different roles and what happens. So the first is the init state, where the two routers exchange their router IDs, and then they move on to the two-way state, where the two routers form OSPF neighborship. And then the next is the xstart state, where basically the two routers negotiate on three factors. One is who would become the master and who would become the slave. The next is the negotiation on DBD sequence number. The third is the negotiation on MTU size. And after these three negotiations have been done, they go on to the exchange state, wherein they exchange each other's DBD. DBD is basically database descriptors. I'll show you this in today's practical. The DBD, as I said, is just a small summary or an index or a small description of the whole database. These are exchanged in your exchange state. And whatever database is required by the two routers, they exchange the whole database in the loading state. And finally, the two routers move into a full state and become OSPF adjacent routers. So in today's video, we are going to look into link state advertisements. Now, what is a link state advertisement? You can see there are different types of link state advertisements starting from 1 up till 8. But before we jump into these discussions, let's first understand what basically is a link state advertisement. We know that OSPF is a link state protocol, and OSPF advertises, you can see it advertises the state of the links that it is connected with, right? So for R1, the links that it's connected to, as per this diagram, are the two loopback addresses that you can see, and one um, IP address that is configured on its serial 4/0 interface. These are the links that it is connected with. So basically, R1 will advertise about these links or the states of these links to R2, and the same would be done by R2 as well. R2 will advertise about its own loopback addresses as well as this IP address to R1. Right. So R1 and R2, they both advertise about these links through different LSAs. You can see there are 8 LSAs starting from type 1, which is called as a router LSA, then network LSA, summary LSA, summary ASBR LSA, autonomous system external LSA, multicast OSPF LSA, not so stubby area LSA, and external attribute LSA for BGP. So in our OSPF series, we will be concentrating only on the first 5 LSAs. Sorry, first 5 LSA and the LSA number 7. So in total, we will be concentrating on 6 different LSAs, right? And in today's video, we are just going to concentrate on the first 2 LSAs, that is the router LSA and the network LSA. Right? Now, what is a router LSA? Let's start with the first one, type 1 router LSA. So every router, every OSPF router generates a type 1 LSA. Okay. So in our diagram, R1 and R2, these are the two routers, and they will generate their own type 1 or a router LSA. And what is inside this router LSA? Let's check that. So as per our diagram, it says that the contents inside a router LSA are these: link ID, advertising router, age, checksum, number of links that it's connected to, and sequence number. So from R1's perspective, in our diagram, from R1's perspective, the link ID that R1 will produce inside the type 1 LSA is the ID or the router ID of R1. Okay. Now, link ID means the router which basically generated this LSA. So in our case, R1 is generating the type 1 LSA, and thus R1 will write its own router ID in the link ID. So router ID is here 1.1.2.1 because the highest loopback address is chosen as the router ID, right? And since R1 itself is advertising this LSA, right? So the advertising router's ID would also be 1.1.2.1. Age. It is the age of it's basically the number of seconds that has elapsed after generating the type 1 LSA is what is mentioned here. So basically it would be some XX seconds, right? And checksum. We know that checksum is used for integrity of the LSAs, or for that matter any uh, protocol. We have a checksum. Basically, it tells the integrity of a particular packet, right? And the number of links that this router is connected with. So here, if you see, the number of links that this particular router is connected to is, as per our diagram, we have 3 links that it's connected to. 2 are the loopbacks, and 1 is this interface. Also, R1, not just R1, any router will consider a serial interface as 2 networks. One as the IP interface as well as the network that this IP address belongs to. So in total, this router or R1 is connected to 4 links. So it would mention 4 links, and the sequence number of this LSA. Sequence number of this LSA will also be mentioned. When I do the practical, I'll show you these things together. So basically, this is your DBD that we saw in our exchange state. In the exchange state, if you remember, the two routers, the master and the slave, they exchange their DBDs. So for R1, this is the DBD. For R2 also, if we see, the link ID would be 2.2.2.1 because R2 is generating its own LSA. So whoever generates the LSA, his link ID would be present. So 2.2.2.1. And since R2 is also the advertising router, so 2.2.2.1 would be the router ID. Age, the time that has elapsed after generating the LSA, that would be mentioned in seconds. Checksum, we know that it's for the integrity. Number of links that R2 is connected to, it would be the same as R1 because 1, 2, 3 and the network that this interface is connected with. So in total 4 and the sequence number of this LSA, right? So in total, R2 is also connected with 4 networks or 4 links. This is the DBD for R2. So let's check this through a practical. So you can see the same diagram that I had in my whiteboard. So you have two routers, R1 and R2, where I have configured OSPF already. I'll show you the OSPF configuration shortly. And the loopback addresses that I have configured in on R1 is 1111 and 1121. The IP address on R1's serial interface is 12.0.0.1/8. On R2, the loopback addresses are 2211 and 2221. The IP address on serial 4/0 of R2 is 12.0.0.2. So show IP interface brief, exclude unassigned. We can see these are the IP addresses on R1 and on R2. Show IP interface brief, exclude unassigned. Sorry, my bad. These are the IP addresses that are configured on R2. I've already enabled OSPF. So if we want to check the uh, configuration on R2 for OSPF, we can do a show run section OSPF. So this is the configuration that I've done on R2. I have given the network command as 0. As I said, it's the laziest command. That means I'm enabling OSPF on all the interfaces of the router, and it's a part of area 0. On R1 also, you can find a similar configuration for OSPF. Probably the network command may differ. Oh, it is the same. So router OSPF 1, 0, 0, 0, 255, 255, area 0. Right. Now, as I was saying, all these routers, they produce their own LSAs. Okay. And to check the LSA, let's go back here. To check the LSA, all we need to do is type the command show IP OSPF database. Show IP OSPF database. So this basically is the DBD database descriptor that not just R1, R2 will also produce his own DBD, right? And this basically is the DBD database descriptor. It's just a small description of the whole database. I'll show you the complete database in a short time, right? So as I was saying, what are the information present inside the DBD? If we see, we have two LSAs present on router R1. R1 has two LSAs. One LSA is produced by itself. The other LSA that was produced was by R2, right? So we can see R1 generated this LSA and R1 itself is advertising this LSA. 214 seconds have elapsed after generating the LSA. The sequence number of this LSA is 080001. So if there are any changes in the network, for example, if R1, I add a new link or a new loopback address on R1, the sequence number would increment to 80002. And if I delete any link, that's a new LSA, so the sequence number would increase. So every time there is a change in the network, a new LSA is generated, router 1 LSA is generated, and the sequence number of that particular LSA increases. That means the higher the sequence number, the latest the LSA is. That's what it means. Checksum is for the integrity, and as I said, your router is connected with 4 links. So this sequence number and this age have a very unique relationship, right? So let's say that I have 3 routers connected in a triangular shape. For example, this is R1, R2, and R3. So now what will happen is, if R1 is sending an update, right, it would send directly to R3, right, and it would receive its update via R2 as well. R3 would receive R1's update through R2 as well, right? So now R3 has the information of 2 LSAs, right? 2 identical LSAs in itself, that is sent by R1. So one LSA it received directly from R1, the other LSA it received through R2. So what would happen is, both the LSAs will have the same sequence number, right? Both the LSAs will have the same sequence number. The reason is R1 has sent that LSA, and there is no change in the LSA. The only difference is that R3 is receiving one LSA directly, the other it is receiving indirectly through R2. The sequence number is going to be the same. So R3 would choose the LSA which has a lesser age. The sequence number is the same sequence number, but the lesser age. So obviously the LSA that R2 is sending would have a more LSA age than R3, because it's coming indirectly through through R2, and hence the LSA that is received indirectly through R2 would have a greater LSA age, and hence the LSA that is that has a lesser age would be chosen over uh, an LSA which has a greater age, right? That is one condition where I said the LSA and sequence number has a relationship. The second is that if 2 LSAs are received, both have the same age. If both have the same age, or irrespective of the age, just forget LSA age for now. If both the LSAs are received and they are from the same link ID router, the LSA with a higher sequence number would be chosen over a LSA which has a lower sequence number. So as I said, as there are new updates created inside a router, the router creates new LSAs. As the LSAs are generated, the sequence numbers are increased. So let me show you that example now. So if you see, the LSA is 537 here, and the sequence number is 8001, right? So if I make any changes, let me add a loopback address on R1. Configuration terminal, interface loopback 3 with an IP address 1.1.3.1 255.255.255.255 IP address. I'm sorry, I missed the command. IP address, and this basically is an update. So if I do a show IP OSPF database, you can see that the sequence number has increased. That means this is a new LSA that has been generated, and you can see the age has been reset, right? So every time there is a change in the network of a router, the router produces a new LSA. If it's a new LSA, the age starts with 0 and the sequence number is increased. So the higher the sequence number, the latest is the LSA, right? And in this case, where R1 is sending an update, R3 has received an update directly from R1 and it is receiving an update indirectly through R2. In that case, sequence number is going to be the same, but the age would vary within the two LSAs. So the lesser age, R1's update that is being sent directly to R3 would have a lesser age than this update, and hence the update that is received directly would be chosen over the indirect LSA. So I explained the relationship of LSA and the sequence number, right? And now let's check what basically is inside these LSAs. Before that, let me also show you the LSA of R2, right? On R2, show IP OSPF database. If you see, R2 also has a very similar database, right? So you can see on R2, it has received an LSA created by R1 with a sequence number 02. So R2 has received a latest LSA, correct? R2 has its own LSA as well as the LSA that was generated by R1. Now, we know that in a link state protocol, all the routers inside a particular area have a similar database. That is why you can see R2 also has a similar DBD, R1 also has the similar DBD, not similar, exactly the same DBD, right? So now this was just a summary of your DBD, right? Let's open the database and see what's inside the description. Okay, but before that, let's first understand that theoretically. Okay, now, but before we move on, since I created OSPF, if I want to check what are the protocols that are running on a particular router, a router can be running different protocols. It can have OSPF, it can have EIGRP, it can have BGP, ISS, lot of protocols. So if you do a show IP protocols, you can see the different protocols that the router is running. And since I'm running only OSPF, I can see only OSPF protocol configured on the router, right? So you can see routing protocol is OSPF with the process ID 1. The router ID for OSPF is 1121. That's the highest loopback interface. And the networks that I'm advertising through OSPF is this, right? You can see that. And let's do a show IP OSPF interfaces. Or let's do a show IP interface first. Interface serial fast Ethernet 0. Right. Sorry. Show IP interface serial fast /0. So I did this command to show you a one particular interesting line, that is multicast reserved groups joined 224.0.0.5. So if you see here, the moment you enable OSPF on a particular interface, that interface joins a multicast group of 224.0.0.5, which basically here is the OSPF. If this router on this interface and this interface was also running EIGRP and ISIS, those protocols' multicast address would also be shown here, right? So you can see serial 4/0, and you can see there its IP address, and the broadcast address for this IP address is 255.255.255, and it has joined the multicast address group of 224.0.0.5. Show IP OSPF neighbors. We can see when I do a show IP OSPF neighbors, we can see the neighbors router ID. The priority is 0. Why is it 0? We'll understand that later. The state, please remember, this is the information of the neighbor, not our router. So I am on R1. This information is of R2, right? So the R2's router ID is 221, priority is 0. R2's state is full. Its dead timer is 36. The address, the interface IP of R2 is 12002, and the interface is serial 4/0. Right? We've already seen show IP OSPF database. This basically is the database descriptor. Now, if you see, the moment I added a new loopback address, you can see the link count has increased to 5. If I delete this loopback address, configuration terminal, no interface loopback 3. And let's do a show IP OSPF database. We can see the LSA sequence number has increased, the age reset, and the link count has decreased to 4. Right? And if we do a show IP OSPF interface, sorry, let me do a brief. We can see these are the interfaces. I'm sorry. I'm sorry, I had some problem with the video. All right. So these are the interfaces on which OSPF was running. We can see these two interfaces are loopback interfaces, and this is a point-to-point interface. And if you remember, as I was saying, on an OSPF, a serial interface is always mentioned as the OSPF network type is mentioned as point-to-point. So if I do a show IP OSPF interface serial 4/0, you can see that you can see the information that this is the IP address of serial 4/0. It's part of area 0, and it's attached by a network command. The process ID of OSPF is 1, router ID is 1121, and the network type of this serial interface is point to point, and the cost of the OSPF cost of serial interface is 64. The hello timer configured on the interface is 10, and dead timer is 40. You can see all these things, right? Similarly, if we check for the loopback interface, loopback 1, you can see the network type for a loopback interface is mentioned as loopback. Cost is 1. Router ID is 1121. That is basically R1's router ID. The address of this loopback address interface is 111/32. Right. Show IP OSPF database. We have already seen that. Now, as I was saying, if we open this database, right, now this database descriptor is for R1. Let's open the whole database of the LSA that was created by R1. To do that, all we need to do is the same command, show IP OSPF database. Now we are trying to open the type 1 LSA. Obviously, the CLI command does not understand type 1 LSA. It understands the router LSA, which basically is the name for type 1. Router LSA for which router? I am trying to open the LSA that was generated by 1.1.2.1. And if you see, this is the whole database of R1. Router LSA database of R1. So we can see that it says the router ID is 1121, process ID is 1, it's for area 0. You can see the LSA age is 197. Link state ID, basically the router ID, right? And since R1 is generating 1121, sequence number can be seen, number of links. So basically, this is your DVD, and the whole is your database. So, as I was saying, the information that can be seen in the whole LSA database is the number of links that is connected to the router. Okay, if you want to see that, we can see it is connected to 4 links. We can see the number of links that it's connected to, right? So it's connected to a stub network, which basically is the router's loopback IP address. If you remember, I had mentioned the OSPF considers loopback addresses as a stub network, right? Stub network, and there its network mask is 255.255.255. It's also connected to another stub network. Basically, it's loopback 2 IP address 1121, right? And it's one of its link, right? The serial interface link, which basically is a point-to-point interface, is connected to a nearing router or a neighbor router whose router ID is 22221, right? And the interface on which this router is connected to is 12001, right? And its cost to reach this router is 64 over this link, right? And it's also connected to a stub network 12000 whose network mask is 255 to 255.0.0.0. So basically, we can see on R1 the number of links that it's connected to, right? So it shows us these 4 links, the information of these links. It's and the link that connects to the neighboring router, right? Network running on those links, cost to reach those links, neighbor reachable over those links, and the IP address of that link. We saw all that in this whole database. So this basically is your database of R1. I can check the database of R2 as well, because R2 has shared his own LSA with R1. So show IP OSPF database, right? So if I want to check R2's database, all I need to do is show IP OSPF database, and I'm going to check R2's router LSA or type 1 LSA with his link ID that he has mentioned. So we can see that R2 is telling R1 what his LSA is, how many links that it's connected to, right? So R1 is saying my LSA I generated, right? Who generated this LSA? 2221. Advertising is 221. The sequence number is 8001, right? LSA age is 1347. Now R2 is connected with 4 other links as well. 2 are its loopback addresses, which basically is considered as stub network by OSPF. It is also connected to a serial interface. That serial interface is connected to another router, and that router's router ID is 1121. This basically is told by R2, okay? And R2's cost to reach this link or this router is 64 through this link, and this link has an IP address of 12.0.0.0.2, right? And it's also connected to a stub network 12.0.0.0.0, right? R2 cost of this stub network is 64. Basically, these two are the same thing. So OSPF considers serial interfaces as 2 links, right? So if we check the cost of R1 to reach R2's loopback addresses, we can do show IP OSPF rib. We can see R1's cost to reach 2.2.1.1/32 is 65. Similarly, for 22221 is 65, and we can see it's the best, and it is also installed in the global rib. Global rib means fib. So if you do a show IP route, which is the global rib or fib, you can see that to reach 2211, the administrative distance of OSPF is 110. The cost is 65 via 12002. How does OSPF create this? Let's check that. It creates basically through the database that R2 has shared. So show IP OSPF database router 2.2.2.1, right? So R2 sorry, let me open the database of R1 1.1.2.1. So to reach 2.2.2.1, right? R1 knows its cost to reach the neighboring router, right? Its cost to reach the neighboring router is 64, right? So, and it can reach this neighbor through 12001, and the cost to reach through this interface is 64. That is done, right? But now it checks for R2's database, show IP OSPF database router 2.2.2.1, right? So R2 is connected to loopback addresses 2.2.2.1, and R2's cost to reach this loopback address is 1. So in total this becomes 64 to reach 2.2.2.21 router, and router 2.2.2.1's cost to reach its loopback address as 1, which basically is what is 65, and that is what is seen on the routing table. To reach 2.2.1.1, the total cost is 65 via 12002. And how does R1 knows it's 12002? Because R2 itself is telling that, right? R2 is saying it is connected to 1.1.2.1. Obviously, this is R1's routing ID, right? Or router ID. And R2 is connected to this particular router through this interface. So R1 already knows to reach the R2 router, its next hop IP is going to be 12.0.0.0.2. This is how R2 has calculated the exit interface. So this is how you can see the LSA1, OSPF database, OSPF DBDs, and how OSPF routers on a serial interface calculate their cost to reach each other. We can see a similar calculation on R2 as well. R2's cost would also be the same. Show IP OSPF RIB to reach 1111, its cost is 65. So obviously we know that the serial interfaces cost for R2s, this would be 64, and R1's cost to reach the loopback address is going to be 1. So 64 plus 1 is 65. Right? Similar calculation would be done by R2 as well. So this was about LSA 1. So we'll check LSA 2 in a short while. If you want, please take a break and you can resume the video. So now let's go to type 2 LSA. So before we jump onto type 2 LSA, let's first understand why there was a need for a type 2 LSA, right? So let's think of this diagram, okay, where all your devices, all your routers, as you can see here, are connected on a broadcast segment, okay, broadcast or a multi-access segment. So here in this case, what would happen is, since all of them are from the same broadcast segment, any message that is sent would be shared with everyone. So if R1 is sending an LSA, right, R1 has to send that LSA and it would be shared across all the devices, right? R2 would also share his LSA, R3 would also do the same, and R4 would also do the same, and R5. All the 5 routers would share their LSAs. So we know that once these LSAs have been shared with each other, they will share the DBDs with each other. After the DBDs, they will start to share the database. So in our previous discussion with type 1 LSA, you could have noticed that both the routers have a similar database with each other, right? So in this scenario, what is happening is that R1 shares his database, it is exchanged with all the routers. R2 shares the same database with all the routers. R3 would do the same. R4 and R5 would also do the same. So basically what is happening is your LSA 1 message is basically flooding in the network, and all of them have the same message, have the same data, right? So what is happening? Increase of your LSA messages has happened. And since there are 5 routers, right? The routers exchange, or the routers have the same database, right? And R1 will share his database with R2, R3, R4, and R5, and so do all the routers. And the same database. What is happening? Your size of the database is also increasing, and all of them have the exact same database, right? So that's one problem in your multicast, multi-access segment. Second problem is R1 needs to create adjacency with all the routers, right? So with R1, it needs to create adjacency with 4 other routers. So does R2 also needs to create adjacency with 4 other routers. So basically 5 times 4, there are 5 routers and they need to create adjacency with 4 routers. So you have 20 adjacencies, and with these adjacency, they need to share these adjacency with all the other routers. Again, there is an increase of data here, right? And we have already discussed, with that there is a flooding of the same database in the whole network. So in order to solve this, right, in order to solve this, we thought, why not have 1 or 2 routers have the same, or why not have 2 routers that have the whole database with them, and let all the other routers get this database information from these 2 routers, right? In order to explain this, let us go back to our childhood memory of classrooms, right? So you can see that there is a teacher, right, and there are a lot of students, and then there is one special kid who basically is the class monitor or a class representative, right? So basically his work is to monitor the class. Whatever information the teacher tells, he needs to share it with all the other students, right? The teacher is not going to share all the information or every information with all the students, but she will share it with this class monitor, and it's his responsibility to share that information with all the other students. That's one. Second thing, we would have noticed that no, 2 students cannot talk to each other. If they need to talk to each other, they will raise their hand. They'll ask the monitor, I need to talk to this guy. Can I talk? So the monitor basically, the class monitor basically gives him the permission, and they two can talk to each other. Right. Second thing, if a student wants to share his notebook with someone else, what he does, he'll give the notebook to the class monitor. The class monitor then takes the notebook and gives it to the other student. So basically what is happening is that this class monitor is basically a very important character, or he has a very important role and has an important responsibility inside the class, right? It's his duty to share all the information with all the students. It's his responsibility to keep a note of what is going inside the class, right? What has the teacher shared with him, he needs to share it with all the students. What the students are doing, he needs to keep a note of it and share it with the teacher, right? So that's the work of your monitor. Similarly, in our scenario, we have 2 important such roles in OSPF. One is called as the DR, or designated router. Designated router, right? So in our scenario, if we see, in our scenario, if we see one of the routers, please ignore this one for now, okay? What will happen is that in our scenario, one of these routers would become the DR, or the designated router, right? So for example, R1 becomes the DR. What would happen is that all these routers will share their database with R1 only. They will not share their database with all the other routers. They will share their database with R1 only. Now, what would happen is that how will these routers know that R1 is the designated router, right? Because if they want to share their database with one such router, he needs to show or he needs to have that capability of being a designated router. So when R1 becomes a designated router, he generates an LSA called as LSA2, which basically is the type 2 LSA, and it's called as the network LSA or LSA number 2, network LSA. And he tells all the other routers in the same multi-access segment that he is the DR and that every router needs to share their database with him only, right? So what would happen is that R1 will share adjacency, okay, will share adjacency with all these routers, will share adjacency with all these routers. But the routers will not have adjacency with each other. They will only create neighborship. They will only create neighborship among themselves. Right. So basically, if you remember when I said the two routers are in OSPF neighborship when they form a two-way connectivity with each other. So all these routers R2, R3, R4 and R5 will be having a two-way neighborship with each other but have a full adjacency with the DR only. Now, what if the DR fails? Right? If the DR fails, who would become the next DR? For that purpose, we said we are giving you a backup. We are giving you a backup, right? So now the routers, for example, the backup designated router is R5 in our scenario. So what would happen is that R2, R3, R4, they will also form full adjacency with the BDR, right? So your routers in your multi-access segment will form full adjacency with DR and BDR. BDR is created in case the DR fails. The backup designated router takes on the role of DR and stores the database information of all the routers. Right. Now, we know that in our classroom example, right, if someone has to become a monitor, a class monitor, right, the teacher has some criteria to make a student as a class monitor, and that criteria would be different factors. Probably he has a good management skills, he can manage all the students, right? Probably he is good at studies. In my days, now the teacher used to make someone as a class monitor if he scores well, if he is ranked number 1, 2, 3, etc., right? So usually the rank number 1 gets the responsibility of being a monitor, class monitor, right? And second rank becomes the assistant class monitor. Similarly, here also in OSPF, you have some election criteria to become a DR or a BDR, right? Now, to become a DR or a BDR, right, the election criteria says that whichever router has a higher priority will become the DR. Whichever router in your multi-access segment has a higher priority becomes a DR. By default, this priority is 1 in a multi-access segment by default. Since by default the priority is 1, the next tiebreaker is whichever router has a higher router ID becomes the DR. The second highest router becomes the BDR. Okay, this is by theory. By theory, this is what it says, and every one of us who has studied OSPF has studied this. Whichever router has a higher router ID becomes the DR, and whichever router has a second highest router ID becomes the BDR. Please keep in mind that the DR and BDR election will happen only in a broadcast segment. I'll show you this in a practical today. Always happens in a broadcast segment. If two routers are connected over a serial interface, DR BDR election does not happen. Okay. As I was saying, in theory, this is what happens. If a router has a higher priority, that becomes the DR. If not, the highest router ID router becomes the DR. The second highest router ID router becomes the BDR. This is by theory. But by process, what actually happens? Let's understand that. Let me assume that all these routers are switched on at the same time, right? The moment they are powered on at the same time, what would happen is that they will assume themselves as the DR. The reason is they will say, we know that the moment we enable OSPF, OSPF automatically knows that it has been enabled on a fast Ethernet interface. And for a fast Ethernet interface, the OSPF network type is broadcast. So what it would do is it would assume itself as the DR. I'm sorry, it does not assume itself as DR. What basically happens is it creates it creates a DR and a BDR router ID by the IP address 0.0.0.0. This basically is your IP address for a DR and BDR in your multi-access segment when a router basically comes up for the first time, right? Now, as I was saying, all these routers are powered on at the same time. So obviously their DR and BDR router ID is 0000, right? Then the next, what happens is that if these routers, for example, not just this router, any router in a broadcast segment, it waits for 40 seconds. That's basically your dead timer. It waits for 40 seconds to hear a hello from any other router in the same broadcast segment. If it does not, if it does not hear any hello from any other router, it assumes itself as the DR. It assumes itself as the DR. But in our scenario, what happened? All these routers have come up together. So they assume themselves, they create a router ID with 000 for a router ID for DR and BDR. Then they start looking for subsets of hello messages where someone is claiming to be BDR. Someone is claiming to be the BDR. Okay. In the first step, what is happening is the router has come up. It did not find anyone as the DR because the reason is it did not find anyone as the DR, right? So it starts to look for the routers which are claiming to be BDRs. It starts to look for routers which are claiming to be the BDRs, right? And all these routers since have come up as have been powered on at the same time. No one is a DR, no one is a BDR, right? But in their hello messages, their router IDs are all zeros for DR and BDR. The next thing that happens is that they will first elect a BDR. Since they do not have any DR, they do not have any BDR, first election happens for a BDR. Whichever router ID has a higher whichever router has a highest router ID, that guy becomes the BDR. That's the first thing. Once the BDR is elected, they start to look for the DR. Who is the DR? Since there is no DR because all of them have been powered on at the same time, this BDR which was elected becomes the DR. This BDR which was elected becomes the DR. And now again, the election for BDR happens with the same criteria. Whichever has the highest router ID becomes the BDR. So by theory, Whichever router has a higher router ID becomes the DR. Whichever router has the second highest router ID becomes the BDR. Is just theory. But actually, what happens? Routers choose BDR first because they are looking for DRs. Since they do not find a DR, then they look for a BDR, right? And then a BDR election happens. Whichever router has a higher BDR, has a higher router ID becomes the BDR. They again look for a DR. They do not find a DR. So the recently elected BDR takes on the role of a DR. Then again the BDR election happens. Whichever router has a second higher router ID becomes the BDR. So this is how your DR and BDR is elected. Now, whichever router becomes the DR out of these routers, whichever router becomes the DR in our scenario, R5 will become the DR because that is what has the higher router ID. 5555 is the router ID. So R5 becomes the DR, and the moment R5 becomes the DR, it sends out an LSA 2 saying that I am the DR and now you guys need to create adjacency with me. R4 will become the BDR. He will not generate an LSA2. He will not generate an LSA2. He will create adjacency with R5, R1, R2, and R3. Similarly, R3, R2, and R1 will create adjacency with the DR. And they know that R1, R2, and R3, they know that since they are neither the BDR nor the DR, they are DR others, and they need to create two-way neighborship with each other. Let's check that in practical. But before we move on to the practical, let's understand some multicast addresses, new multicast addresses. The DR other routers, which are neither the DR nor the BDR, right? Those routers are called as DR other routers. In our scenario, R1, R2, and R3 are the DR other routers. They send updates at the multicast address of 224.0.0.6. Why? The reason is that if they send the updates at 224.0.0.5, which will be received basically by all the routers, because 224.0.0.5 is the multicast OSPF address. 224.0.0.6 is the OSPF DR multicast address. So any updates that R1, R2, R3, and even R4 shares is at this address 224.0.0.6, and it will be heard only by your DR router. Right? When your DR responds, he will respond at the multicast address of 224.0.0.5 because that message has to be heard by all the OSPF routers. Right? So the moment you have a multi-access segment, you have two multicast addresses. One is 224.0.0.5 and 0.6. 6 is the multicast address where all the DR other routers send information to DR and it can be heard only by the DR. 224.0.0.5 is the multicast address at which the DR responds to all the OSPF routers. So let's check this in a small practical. So you can see in this diagram, I have 5 routers connected through a switch, and they are in a multi-access segment, and the IP address is 10.0.0.0/24. Right? You can see their IP addresses. R1's IP address is 10.0.0.1. R2's is .2, .3, .4, .5 respectively for R3, R4, and R5. Their loopback addresses are 111, 222, 333, 444, and 555. Right? And I've enabled OSPF on them. So the moment I enable OSPF on them, okay. So on R1, let's do a show IP protocols. Right. As I was saying, as I was saying, on R1, we can see that R1's router ID is 1111, right? It is a part of OSPF process ID 1, and the network that it's advertising is 000 255 area 0, and you can also see the next hop IP's router IDs, and the administrative distance is 110 110 110, right? And on R1's show IP OSPF interface fast Ethernet 0/0. This is a fast Ethernet interface, and you can see that the OSPF network type is a broadcast. So whenever the network type is broadcast, that's where you will always have a DR and BDR election. We can see the cost is 1 for this. The hello time and dead timer remains the same, 10 and 40. Right. And let's check the show IP OSPF neighbors. We can see that R1 has a full adjacency with the DR and BDR. Basically, the DR is 5555 because R5's loopback address is the highest router ID, and hence R5 becomes the DR and R4 becomes the BDR. Right now, R4 is the BDR. It has created a full adjacency with DR and BDR, and we can see that it is having a two-way neighborship with DR other routers, that is router 2 and router 3. Right. Similarly, we can check on R2 as well. Show IP OSPF neighbors. We can see R2 has a two-way neighborship with DR other routers, that is R1 and R3, and it has a full adjacency with the DR and BDR. On R5, which basically is the DR, let's check what changes can we see on the DR. We can see it has full adjacency only with the BDR. Sorry, it has full adjacency with all the other routers. Right? Whereas the DR other routers only had two-way adjacency with DR other routers, but the DR has full adjacency with all the routers. So now on R5, if I check the database, show IP OSPF database, right, we can see now there are two LSAs generated. As I was saying, LSA 1 is generated by all the routers, irrespective of what the network type is. It is created by all the routers because LSA 1 is proprietary to a particular router. It is telling about its link that it's connected to through LSA 1, and hence all the routers will generate their own LSAs, and we can see, you can see 5 router 1 type 1 LSA or router LSAs in R1's database. Right, you can see their ages, you can see their sequence numbers, checksum, and the links that they are connected to. Right now, if I open show IP OSPF database router LSA for 1.1.1.1, right, this is R1's router LSA. We can see that R1 is connected to two networks. One is a stub network, that is its own loopback address. The other, it's connected to a transit network. Transit network means a multi-access segment, right? In that multi-access segment, the designated router is 10.0.0.0.5, and if R1 wants to reach this designated router, the interface IP that it needs to send out is 10.0.0.0.1. We can see that a similar information would be present or given by R2, R3, R4, and R5. I can check the same on R1's database itself. So instead of 1111, 2.2.2.2, because that's what R2 said, and R2 is saying to reach the multi-access segment, its router interface is 10.0.0.0.2. So R1 already knows if it needs to reach an IP address which is connected or which is connected with this link ID or the router which generated this database, its next hop IP is going to be 12.0.0.0.2. R2 is saying my link ID is 22222, right? And I am connected to a transit network whose designated router is 10.0.0.5. This is designated router ID, sorry, IP interface, right? And I am my router interface IP address is 10.0.0.2. Similarly, we can find that for R3 as well, 3.3.3.3. It would say 10.0.0.0.3. R4 would also say the same thing, 4.4.4.4. So R1 already knows if it needs to reach these routers, what the next hop IP is going to be. So show IP route. So if you see here, to reach 2.2.2.2, it is 02. For 3, it is 03. For 4, it is 04. And for 5, it is 05. So all these routers have already mentioned their own interface IP in their LSA1. Right now, on R1, show IP OSPF database, we also see a LSA2 also, right? So in LSA1, the difference between LSA1 and LSA2 is in LSA1, these are the router IDs of the routers who generated these LSAs. But in LSA number 2, this basically is the interface IP of the DR who generated this LSA number 2, right? And R5 is generating this, and 588 seconds have elapsed. Now let's open this. So to open the LSA number 2, just like your router LSA, instead of a router LSA, we need to give network LSA. Network LSA for 10.0.0.5. This basically is the information present in your LSA number 2. Right? It says it's a part of OSPF process 1 and 1.1.1.1, because we are on R1, this is R1's router ID, right? And this LSA number 2 is for area number 0, right? And we can see that for 10.0.0.5, what is the address mask? It is /24. So it already knows the number of IP addresses that can be part of the same segment, same multi-access segment, right? So no matter what router ID I say, 10.0.0.5 up till 10.0.0.254, all of them will be part of the same multi-access segment. How does the router know? It already knows through the LSA number 2. And this LSA number 2 was sent by DR to all the routers. So all the routers already know that they can reach to any router with a subnet mask of /24, because all of them are part of the same multi-access segment. And through their LSA once, they already know what is going to be their next hop IP. Right? So let's see when LSA number 2 is generated. I can see LSA number 1. Let me open the Wireshark. Because this is a multi-access segment, I can open any link. It will have the same information. All the links will have the same information. So we can see that all the routers are producing LSA, or are sending, not LSAs, they are sending hello messages, right? Now, if we want to see when LSA number 2 is generated, let's do this. On R5, let me shut down the IP interface for R5. So configuration terminal, interface fast Ethernet 0/0, shut. Right. Now, the moment I shut down the IP interface on R5, R4 would become the DR because the backup designated router would become the next DR. So the moment I did that on R4, let's open R4's packet. So you can see R4 has become the DR. So the moment R4 became the DR, all the routers need to exchange their database with R4. So how did R4 say that I am the DR? Basically, what was happening till now, the BDR, basically the backup designated router, was waiting for 40 seconds of dead interval time. And after that only your routers started to exchange their database with each other. Right. So now on R4, if you see on R4, see here on R4, if you see here, it says that it has become the DR, right? It says it has become the DR. If you see here, these times are a bit jumbled, right? So R4 has created a type 2 LSA saying that I am the DR. Advertising router is 4444, right? And it is saying that I am the DR, and now that you need to share your database with me. So now what is happening? These routers are sharing their database with R4 since it has become the DR, right? So every time a router becomes a DR, it creates an LSA2 saying that I am the DR and now you need to exchange your database with me. So if I bring back this interface, configuration terminal interface fast in 0/0, no shut. R5 will not immediately become the DR. The reason is that there is already a DR and a BDR present. Okay, so if a new router joins the network which has a better router ID, it cannot become the new DR. The reason is there is already a DR and BDR present. And until unless the current DR and BDR fails, the new router which has a higher router ID, until unless the current DR and BDR fails, the new router with a new higher router ID cannot become the DR. So if we check the neighborship of R5 with other routers, show IP OSPF neighbors, you can see your DR is R4, BDR is R3, and DR other. So obviously R5 is a DR other. So if we do a show IP OSPF interface brief, we can see that R5 is a DR other. We can also see that it has formed adjacency with two routers. Why? Adjacency is only with two routers because it's the DR and the BDR, and the neighborship is with four routers, right? Neighborship is with four routers. So if you open show IP OSPF interface fast Ethernet 0/0, we can see the neighbor count is 4, adjacency count is 2, and who is the DR, who is the BDR, and who is the DR. We can also check these information there. Now, if I want R5 to become the DR once again, I need to shut down R4, When I shut down R4, because that's the current DR, the moment I shut down R4, R4 will R3 will wait for 40 seconds to become the DR. R3 will become the DR. R5 will then again become the BDR. So on R4, configuration terminal, interface fast Ethernet 0/0, shutdown, right? The moment I do a shutdown, now on R5, if we do a show IP OSPF neighborship, show IP OSPF neighborship, we'll see we are waiting for the DR to go down for the next dead timer. And let me bring down this 7, 6, 5, 4, 3, 2, 1. The moment it goes to 0, we'll see some events on Wireshark. R3 became the DR, right? And now a BDR election is happening. R5 will become the BDR. The database will be exchanged with R5 as well, right? So on R3, let's check R3's information here. Did R3 created an LSA2? We can see it created an LSA2 saying I am the DR. Right. So whenever a router becomes a DR, then only it creates an LSA2. The moment it becomes the DR, it creates an LSA2 so that all the routers know which is the DR, and that's where they all need to share their database with. So this was our discussion on LSA number 1 and LSA number 2. Right. Let me show you the database. Did I show you the database? I think so. Yes. So show IP OSPF database. Right. We can still see our R4's database there. I'll tell you the reason why do we see R4's database. Show IP OSPF. The reason we see R4's LSA number 2 here as well is that LSAs are deleted only when they cross an age of 60 minutes, right? Basically 3600 seconds. The moment this goes to 3600 seconds, this LSA will be deleted. Okay, but still, if we check the show IP OSPF neighbors, we'll see that the DR is R3, BDR is R5. There is no connectivity with R4. There is no connectivity with R4. The reason is the LSA is old, right? The LSA is old, and hence they will not be sharing any information with R4 anyway. Even if they share, this interface is in a shutdown mode. LSAs are not going to go to R4, right? Once this age goes up till 3600, this particular information would also be removed from the network. Or if I bring back R4's interface, configuration terminal, interface fast Ethernet 0/0, no shut. We will see OSPF adjacency coming up and all the routers sharing adjacency and neighborship with R4. And if you do a show IP OSPF database, we'll see that R4's LSA number 2 is no more present. So in order to remove the LSA, the age should cross 3600 seconds in order for it to get deleted. So this was our information on LSA number 2 and LSA number 1. I hope this was very informational, and please do like, share and subscribe to this channel to help me grow. Thank you and have a great day.